Well, this- Dr. Powell. Let's take a look at how we can find the row and column operation matrices while we're trying to find Smith normal form. Now, let's suppose that we have some steps that take us from a matrix A to its Smith normal form. We've done some row operations and some column operations. Now, this is computer generated randomly here, steps that take us from here to here. So perhaps there might be other ones and more efficient ones, but let's try to follow these steps right here, or looking at these steps, try to find the row and column operation matrices that correspond to these steps. Now, if we do different steps, we'll have different row and column operations matrices. But the main part about it is that we find our row operations matrix and our column operation matrix, and we multiply R times A times C, we should get S. Okay, so what we do is we pick out, to find the row operations matrix, we pick out everything that corresponds to rows. So this one right here, row, and this one. So we have two, all right? So then we think, how many rows do we have? We have two rows. Okay, so two rows, and if we think in a column interpretation of matrix multiplication with these matrices being like functions, this happens after A. This is like C happens as a function first, then A, and then this guy. The output of A is in R2 because the columns have two entries in them. So this right here will be an isomorphism on R2 itself. From R2 to R2, it will be a matrix of size 2 by dimension 2 by 2, 2 by 2 matrix for R. Look at the number of rows, and that tells you the dimension. This guy, it's going to be a square matrix. R is going to be a square matrix. C is going to be a square matrix. So, and we can just count the number of rows. There's two. So we know this R is going to be a 2 by 2 matrix. So how do we build R? Well, realize that these guys are really linear transformations on the columns. Now, if we want to get a matrix that describes what they do, we just need to see where does E1 go and where does E2 go. Well, that's the same thing as doing these row operations right on E1 and right on E2. And that tells us our matrix for R. So we start with the identity matrix, 2 by 2 matrix, and we just do these row operations to it. All right, so this first thing says to multiply, so to do -1 times row 2 and add that up to row 1. Okay, so that would give us 1, -1, 0, 1. Okay, next it says to swap rows 1 and 2. So swapping them, we have 0, 1, 1, -1. All right, we have successfully found the row operations matrix. So R is equal to 0, 1, 1, -1. Okay, so now let's try to find our column operations matrix. All right. So it's done the same way, but now we're going to do it on a 4 by 4 and with the column operations. 4 by 4 because if we think about it with a column interpretation, this is a function, tells us where E1 goes, E2, E3, E4 goes. Wait a minute, E4. There must be 4 basis elements. The domain is R4, and C represents an isomorphism, a bijective linear transformation on R4, from R4 to R4. So it's going to be a 4 by 4 matrix. You can also see that the number of columns is 4. 1, 2, 3, 4. So we're going to take a 4 by 4 identity matrix, because then we're going to see where E1 goes, where does E2 go, where does E3 go, Where's E4 go? Okay. And we just apply our column operations. So here, let's figure out which ones are columns. So this guy, and that guy. Okay. So I'm going to swap the first two columns. So swapping these, in fact, we can just do it right on the matrix itself. So that would give us, so if we swap them, B1, 0, okay, because we can see what the steps are right here. So we're just going to do it right here. So we swap those guys. Here's swap columns 2 and 3. Okay, swap those two columns. All right. So that means maybe 0, 1. And then those two guys swapped. Okay, so it's that. Okay, so we've just swapped columns 2 and 3. Now let's add column 2 times column 2 to column 3. So we take 2 times column 2 and we add it to column 3. Well, what the effect is we're going to get a 2 right here. And we're done. So there's our column operations matrix. Here's our row operations matrix. Let's verify that this is actually equal to S when we multiply it through. Okay, so we're going to say R times A times C. Let's first do R times A. Okay, now if we do, okay, so if we do this, we do R times A. And let's think of a row interpretation of matrix multiplication. So we take this row and so what's going to be on the first row of the output when we multiply R and A? It's just going to be 0 times the first row plus 1 times the second row. But pretty much we're going to pick out the second row right here to be the top row of the output. So 0, 1, 0, 0. Then here, what does this mean? That means the bottom row is going to be the first row minus the bottom row. So if we do that, we're going to get negative 2, 0. Let's see, hold on a second here. So we got we have the first row. Yes, that's right. So we have the first row minus the bottom row. So negative 2, 0, and then we just have 1, 0. Okay. All right. Okay, so now we take this is R times A, and we're going to multiply it to C. All right. So we'll do a column interpretation here as we, I guess we could do either way. We could do column or row. Actually, row might not be too bad. So row would be, we take this times that, and this right here picks out the second row. So the output's going to be 1, 0, 0, 0. And then this guy right here is going to say negative 2 times the top plus 1 times the third row. So if you have negative 2 times this row plus this row, notice the negative 2 and 2 will cancel. You're just left with 0, 1, 0, 0. Hey, that's what we wanted. Okay, so we were successful. So we have R times A times C is equal to S, and we're done. Thanks for watching.